In the last class, we have seen the context within which the Big Bang theory has to be studied. According to Big Bang theory, at first, everything began with what is called as a singularity. Now, what is meant by singularity? It means that the time and space were set at zero. Now, what does this mean? Remember, this entire concept of time and space to be set up at zero can be explained by Einstein's theory of relativity. And Einstein's theory of relativity says that the space and time are unalterably linked to form a space-time continuum, which means that there can be no time when there is no space. That means when the universe has begun, all the matter and all the energy were compressed into an infinitesimally small, very high temperature and high density state in which both time and space were set at zero. Now, to simplify this complex text in a nutshell, this means that Big Bang theory explains evolution of the universe in which a dense and hot state was followed by what is called as expansion, and this was followed by what is called as cooling, and this was then followed by getting into a less denser state. These are the stages through which the entire universe has been through. So according to this theory, our universe began when a cosmic explosion took place around 13.8 billion years ago, and all matter and energy that was compacted into a single dense point at that time led to the explosion. And this explosion is not just a burst of matter into the space, but rather, as this theory clearly points out, this is an explosion of space itself. This must be remembered. I repeat, it is not just the burst of matter into the space. Remember, it is rather an explosion of space itself. However, when time began with this explosion, the developments can be marked in various stages with respect to time dimension. Immediately after this explosion, or at the point at which the explosion has occurred. So, to understand these stages, we shall make certain fundamental concepts very clear first. What are these very fundamental concepts which are required to understand Big Bang theory? Look at the way the physics research has progressed. The first dimension that we must look at as part of this conceptual understanding related to Big Bang theory is what constitutes matter. We know from physics that matter is made up of atoms, and atoms in turn are made up of what is called as electrons and nuclei. So we understood that these constitute fundamental particles within an atom. Apart from that, we also know that the electrons have electric charge which is negative in nature, and their mass is very small in comparison to that of the nuclei. And we also know that the nuclei are made up of protons and neutrons. So as far as we know, electrons constitute elementary particles within an atom. And apart from this, we also know that from the so-called standard model of particle physics, which is strongly supported by much of extensive experimental results, suggests that the material universe is assumed to be built by much more small number of fundamental particles, not just electrons, protons and neutrons. They are made up of some very small number of much more fundamental particles. They are called as quarks and leptons. Quarks and leptons are the fundamental particles that actually make up the entire universe. The quarks bind together through what is called as strong nuclear force. Strong nuclear force, or which is also referred to as strong interaction, to make, for example, protons and neutrons. That is the reason why we call them the fundamental particles. Apart from this, we also know that leptons do not take part in this what is called as strong interaction, or they do not react to the strong nuclear force and only interact via what is called as electromagnetic and weak nuclear forces. Quarks, at least in normal circumstances, exist only in bound states. So leptons, on the other hand, can be individually observed. So these constitute what is called as the fundamental particles. Apart from this, there is second aspect that we must know. What is the relationship amongst these constituents of matter in terms of what is called as force? That's what we were trying to address even when we were looking at what really constitutes matter. So the second question is to know the relationship amongst the constituents of matter in terms of what is called as force. The forces which we see in our day-to-day life, like muscular force, frictional force, or forces due to compression and elongation of springs and strings, or the forces such as fluid pressure, gas pressure, electrical force, magnetic force, or interatomic force, and even intermolecular forces are, remember, derived forces, as their originations are due to a few very fundamental forces in nature. What are these few very fundamental forces that we have as part of nature? The first and foremost important force that we have to observe here is the gravitational force. Even if you observe, the gravitational force was the first principle of nature in terms of all these forces that was discovered by Isaac Newton. It is the force of mutual attraction between any two objects by virtue of their masses. It is a universal force, as every object experiences this force due to every other object in the universe. However, you must remember that it is the weakest of all the forces that are offered by the nature. It is also the attractive force which arises from the gravitational interaction amongst these various objects. However, when considered for massive objects like the sun or giant planets that we know, gravitational force is considered to be as strong as the masses of these objects. The phenomena such as the revolution of the moon around the earth, and also the phenomena such as the formation of tides in the ocean, are all due to the gravitational forces of attraction that are acting on various objects because of the sheer massive size that they have. The second important force apart from gravitational force that we must know is the electromagnetic force. The electromagnetic force. What is this electromagnetic force? Remember, the electromagnetic force is particularly between the charged particles. See here, from understanding the forces between massive objects, we have dropped ourselves down to the forces between particles, particularly the charged particles. Charges at rest have electrical attraction between unlike charges, and they also have the repulsion between the like charges, as we know. So the charges in motion, whichever that we are referring to, produce magnetic force. So whatever the forces that we are seeing here getting generated together, hence are called electromagnetic force. So these forces, I repeat, are between the charged particles. There is third force that we must remember, which is called as the strong nuclear force, or as we were referring to earlier as strong interaction. It is the attractive force between protons and neutrons in a nucleus. That means two protons or few more protons and two neutrons or few more neutrons are attracting with each other. So it's a charge independent and acts equally between a proton and a proton, a neutron and a neutron, and also a proton and a neutron. This is the reason why even when we know that electrons are revolving around the nucleus and there is a strong forces which are acting within the nucleus, we don't see the nucleus getting disintegrated or electron just thrown out of the atom because of its motion. Hence, strong nuclear force is one of the very fundamental factors why we see the entire matter being intact. Apart from this, recent discoveries have shown that protons and neutrons, as we know, are built up by these fundamental particles called quarks. So this is how the quarks exhibit the strong nuclear force, because of which we see the formation of these protons and neutrons. The fourth force that we must know is the weak nuclear force, or which is also referred to as weak interaction. Remember, this weak interaction or weak nuclear force appears only in certain nuclear processes. In these nuclear processes, what we find is there are certain elements which emit radiation on their own, and this entire phenomenon of emission of radiation by their own properties is called as radioactivity. This radioactivity as a phenomena occurs in elements known as radioactive elements. Remember, this field was developed by some of the scientists such as Madame Curie and Rutherford. It was observed that there are three kinds of rays, that is alpha, beta and gamma rays, which are emitted. Rutherford found that alpha rays consist of high energy particles carrying 2 units of positive charge and 4 units of atomic mass, which is similar to what is called as helium. So he concludes that the alpha particles are helium nuclei, as when alpha particles combined with 2 electrons yielded the helium gas. Similarly, the beta rays are negatively charged particles similar to electrons, and the gamma rays are high energy radiations like X-rays, which are neutral in nature, that means which don't have any charge. So they do not consist of any particles. So as regards the penetrating power, alpha rays are the least, followed by beta rays and then the gamma rays. So entire phenomena of this weak nuclear force is applicable to these radioactive elements. And remember, it is the weak nuclear force which is also responsible for what is called as fusion and fission as part of the nuclear interactions. Hence, whatever the generation of energy or emission of energy that occurs in stars, neutron stars, the black hole, are primarily because of this weak nuclear force. So we know that the gravitational force is applicable throughout the infinite range, and it is applicable to all the objects which are there in the universe. However, we know that this weak nuclear force is having very short range, and it is having this short range of the nuclear size. Hence, it is particularly applicable to very subatomic particles. Thirdly, the electromagnetic force is also applicable in the infinite range, because all these charged particles are seen everywhere in the universe, and hence electromagnetic force occurs everywhere in the universe amongst all these charged particles. Fourthly, the strong nuclear force again has a very short range, because they occur within the nucleus, and hence it is applicable only to these particles which are there in the nucleus, and also the fundamental particles which try to form these particles, subatomic particles such as protons and neutrons. Here we must remember that the physicists have tried to combine a few of the above fundamental forces, and this combination of forces is what very fundamental in the evolution of this Big Bang as a theory, and also the evolution of the universe. The third important aspect that we must know here, again as part of the conceptual understanding related to the Big Bang theory, is are all physical properties applicable to both particles and radiation, that is matter and energy. This third concept is very important, because this fundamentally explains the very complex nature of the fundamental particles which make up this entire matter or the entire universe. So while striving to better formulate a theory which can explain the salient features of the structure of very complex atoms, physics has tried to move towards what is called as quantum theory, or sometimes it's also in simplistic terms referred to as quantum mechanics. Remember, classical mechanics, which is based on Newton's laws of motion that we were trying to understand in the first phase, or with respect to the force of what is called as gravitational force, successfully try to describe the motion of all macroscopic objects such as the falling stone or the orbiting planets, etc., which have essentially a particle-like behavior. However, this classical mechanics, which is based on the Newton's laws of motion, fails when it is applied to the microscopic objects like electrons atoms, molecules, etc. So this is mainly because of the fact that classical mechanics ignores one very fundamental and most important concept, that is the dual behavior of matter. This is dual behavior of matter. What does this mean? That is both matter and also radiation. Both matter and radiation have what is called as characteristics of both wave and particles. In general, we know that light acts like a wave, which we can understand through these phenomena such as diffraction, and also at the same time light behaves like a particle when we understood this cathode ray tube experiment, in which electrons are to be understood as the fundamental constituents of the entire light. So this behavior of having a wave-like property and also particle-like property is applicable to radiation. Similarly, even the matter or the fundamental constituents of matter behave both wave and particle properties. Basically, this determines that the light exists in discrete quants of energy, which is called as photon. There is one more principle that you must remember, which is called as Heisenberg uncertainty principle, which is also fundamental in understanding the earlier phases of the evolution of the universe. Here, the Heisenberg's uncertainty principle states that it is impossible to determine simultaneously the exact position and the exact momentum or velocity of an electron simultaneously or at the same time. That means one of the important implications of this particular principle is that it rules out the existence of definite paths or trajectories of electrons or any other such similar particles. How it is relevant for our understanding of the evolution of the universe. When this universe has begun with what is called as Big Bang explosion, we know that the trajectories were there for these fundamental particles which made up this entire universe. What sort of trajectory was there, how they were behaving, is probably explained by this Heisenberg's uncertainty principle. So Heisenberg's uncertainty principle and the dual character of having both the properties with respect to matter and light are very fundamental in understanding the earlier phases of evolution of the universe. So in a nutshell, the entire matter being made up of certain fundamental particles, number one. Number two, the four forces which can be observed today as part of the nature, and number three, the behavior of the entire matter and also light possessing what is called as the behavior of both particles and the wave simultaneously are the three fundamental concepts which must be part of the evolution of the universe that we have to study as part of the Big Bang theory. So when we study the Big Bang theory, as we know, the explosion has occurred, and this explosion was followed by what is called as the high temperature and high dense state towards expansion, and then further cooling down in temperature, and then reaching a less dense cool state that we see today. However, as we know, all these occur as a phenomena, as a process. This can be applied now to the understanding of the Big Bang theory by applying even the three fundamental concepts that we have studied. From 0 point, that is the point at which the explosion started to occur, to point of 10 power minus 43 in terms of time dimension, that is 0 seconds to 10 power minus 43 seconds. What we have seen here is the universe is of minuscule size, number one. Number two, the temperature of the universe is very high, at probably 10 power 32 Kelvin or more than that, which is a billion, trillion and trillion degrees. And number three, at such high temperature, and having such a minuscule size for the universe, all forces hence must have been united into one single force, which is called as grand unification. And this transition phase that we see at 10 power minus 43 seconds is called as grand unification transition. And as we know that this entire universe now is having a minuscule size containing within itself the constituent particles which really make up the entire universe, and number two, which also constitutes what is called as the fundamental forces of nature, and also having both wave-like property and also the particle-like property. Remember, this is what the quantum mechanics is, and hence the physics is searching for what is called as quantum gravity, which is what the quantum particle which would really mediate this entire universe into a singular force, which is what is called as singularity. And hence this theory at this particular stage of 10 power minus 43 seconds, if we can develop that theory, is probably regarded as theory of everything. The physics now is trying to develop this theory of everything, and lot of advancement has already been made in the evolution of this theory of everything. So from 10 power minus 43 seconds, now we can move to 10 power minus 36 seconds, and still it is, remember, the grand unification phase only. Here at this particular stage, remember, the temperature now has cooled down to 10 power 29 Kelvin. So after the explosion, as I told you, it is the high dense and high temperature state which has to lead to an expansion and then reduction in the temperature. Now you see a small reduction in the temperature in terms of whatever the reduction that we are seeing here in comparison to the earlier temperature. And at this particular point of time and at this particular temperature levels of 10 power 29 Kelvin, the gravity could decouple itself from the other three forces, which can collectively be now can be called as the electromagnetic force. So this breaking of forces occur because, as I told you, universe has cooled down below the transition temperature. Now you can move to the 10 power minus 32 seconds. Here this particular phase has seen decoupling of strong nuclear force from the other two forces, leaving together hence weak nuclear force and electromagnetic force together. This was possible probably because the universe has cooled down even below the 10 power 29 Kelvin, and at this particular juncture, remember, the universe also has started expanding itself, and hence this particular phase came to be regarded as inflationary epoch, and what we have experienced in terms of universe is regarded as inflation. Here this magnitude of inflation or probably the expansion cannot be imagined because it could expand by an incredible factor around 26 orders of magnitude, meaning a molecule becoming an object of the size which is 10 billion light years across, which means 80 trillion kilometers. Now you can imagine how from 0 seconds to 10 power minus 32 seconds, the universe which is of the grand minuscule size has become the grandest size possible. This is where this particular epoch came to be regarded as inflationary epoch. Now we can move forward to the 10 power minus 12 seconds. At this particular juncture, remember, we must understand that the quarks started appearing. This epoch hence came to be regarded as quark epoch. Electromagnetic and weak nuclear forces have separated at this particular juncture, and hence at this particular point of time, the four forces that we know today have separated and separately existing, and this was possible because the temperature has fallen down to 10 power 12 Kelvin, and hence at this particular juncture we see for the first time mass seems to be occurring. Here still no protons and no neutrons could be developed. However, this is the stage where highest energy epoch that we can really probe in terms of experiment can be seen. This is where large hadron collider experiment comes into picture. It is trying to understand clearly this quark epoch in experimental terms, and this is where we could develop what is called as Higgs boson particle, which is also regarded as God's particle, which is one of the fundamental particles in the evolution of the entire manner. Now we can look at 10 power minus 6 seconds. By now the temperature has cooled down to 10 power 10 Kelvin, and hence the entire universe now has seen the development of what is called as hadrons out of what is called as quarks. As you know, quarks are the fundamental particles which try to then combine themselves to form protons and neutrons. These protons and neutrons collectively came to be regarded as hadrons. So the quark hadron transition could be seen from 10 power minus 6 seconds to 1 second. So by now you see that universe has further expanded. Here now, from 0 seconds to full 1 second after the Big Bang, so much of development has occurred. That means within that short span of 1 second, you see the entire universe coming into being, the forces getting separated, and the particulate matter, which are the fundamental constituents of the entire matter, have also appeared. From 1 second to 10 seconds, what we see is what is called as Lipton epoch. This entire epoch is called as Lipton epoch. What is this Lipton epoch? Here, from 1 second to 10 seconds, whatever those protons and neutrons which have been formed, remember they will also have their adjacent particles which are regarded as antihadrons. As you know, protons and neutrons collectively regarded as hadrons. They will also have their simultaneous particles which are of opposite charge, which are called as antihadrons. They always annihilate each other, and here when they annihilate each other, they try to leave behind what is called as leptons and antileptons, and which definitely dominate. What are these leptons and antileptons? Now you remember, these leptons and antileptons are again the fundamental particles which make up the matter. Now you are getting the point that from 1 second to 10 seconds you have the existence of hadrons and also leptons, and before that even the quarks. This is how the fundamental particles have made up the universe. From 10 seconds to 17 minutes, what you see is the Big Bang nucleosynthesis. What is this Big Bang nucleosynthesis? By now you find that the nuclear fusion must begin. Why? We have seen that the temperatures have cooled down further to 10 power 9 Kelvin to 10 power 7 Kelvin. Remember, this is cool enough for all these protons and neutrons to be stable and hot enough for them to fuse. So what we find here is the protons and neutrons fuse together to make lots of hydrogen and helium, and here because of the coming together, whatever the hydrogen and helium which are formed, and they also further lead to the trace amounts of other light nuclei such as lithium. So the nuclear fusion has begun, which is the fundamental stage for further evolution of the other celestial objects such as galaxies and stars. So from 17 minutes onwards, we find that it is too cold for fusion, and hence the hydrogen and helium remain in the universe. They seem to be having a particular ratio of their existence, and they have existed in the ratio of 3:1. And this has continued for many years. So by now universe is 600 light years across. So over the next several 100,000 years, universe expands. All of these hydrogen and helium nuclei hence try to collect themselves to form what is called as clouds. So this is how you find that the quarks combine to form the protons and the neutrons, and these protons and neutrons also combine, and also you find that they lead to the formation of hydrogen and helium, and further these hydrogen and helium clouds, whatever they combine themselves together, will lead to continuously the nuclear fusion, and this nuclear fusion continues for few millions of years, and hence when they continued for this some of these years, you find that the universe is becoming somewhat structured. So the denser regions are becoming more dense and empty regions become more empty as this epoch has continued, and this epoch is regarded as the photon epoch. That means the light energy has invaded and pervaded the entire universe because of this nuclear fusion, as we see continuous release of energy. So matter and energy are occurring at the same time. Hence this epoch is going to be regarded as photon epoch. From 3,77,000 years to 150 million years, this particular epoch is called as recombination epoch or recombination era. So here what we find is the universe is cool enough finally for electrons to combine with nuclei to form what is called as neutral atoms. So at 4000 degree Kelvin, the universe becomes, hence because of this occurrence, visible, in the sense that we consider that to be transparent to the eye rather than opaque. That means energy is also cooling down and it could be seen by the naked eye if we were existing then. That is the stage at which the world has now entered. So up to 150 million years, except this, nothing much has happened. Hence this is also probably known as dark age. As we see, there is plenty of hydrogen and helium that we must remember. We should not forget that. And at the same time, photons were moving at a faster pace in this particular period up to 150 million years because of the release of energy, because of the nuclear fusion which is occurring. And also we must remember that electrons have combined with nuclei to form these nuclear atoms, and which also further releases these photons as part of light energy which is getting released. That means the clouds which are coming together in terms of hydrogen and helium is seeing the coming together of protons, neutrons and also the electrons, and because of which we see that there is continuous commingling of this entire clouds. Hence the stage probably is set for the production of stars within the universe. So the temperatures have further cooled to 300 kelvins from 4000 Kelvin, which would probably even allow liquid water to exist if there were any liquid water to be available. So, and all the clouds of hydrogen and helium, as we know, continuously collect over the million of years, and this continuous collection was probably because of the gravity that they exert, and as they collect and pull together whatever the matter that they have, much more gravity is exerted by the dark matter now that they pull, and because of this the huge lumps of clouds getting formed, and these huge clumps of clouds which they form, they pull together much more clouds towards them, much more matter towards them. They pull closer and closer until all atoms which are there at the center are pushing right against each other, much more compact and dense. So when there were enough atoms together, increasing density and will exert inward gravitational force, and here because of this the latent heat will rise, leading to the ignition at one particular point. So this particular stage is probably the stage at which the stars would be born. However, you must also remember that the clouds have become much larger in size by now because of the continuous pulling together the matter simultaneously, probably having the size of 1 light year diameter. So this entire cloud of gas that we are seeing of hydrogen and helium is regarded as nebula. This you must remember, which is called as nebula. So here is the stage. You find that the size has increased so high that gravitational pull wins over the kinetic energy of the cloud, which is spinning because of continuous pulling together of matter towards the center. So at this stage the atoms hence are ionized because the temperatures rise at the center a lot. They get too hot for the neutral atoms to exist. So inner regions get hot and further hot, and outer regions would exert much more pressure for these atoms to collapse. And this is what the stage where you see the formation of what is called as protostar. And from this stage of formation of protostar, which is probably in a temporary equilibrium, further addition of matter increases the mass and density further, which leads to the increase in the temperatures further. So, and the temperature becomes so high that fusion starts occurring, and when this fusion starts occurring from the point where the atoms become hot and leading to the occurrence of such a nuclear fusion, we see the tremendous release of energy, and this is the stage where the star will be born, because it is continuously now seeing the occurrence of nuclear fusion. So when the star is born, the radiation ionizes surrounding nebulae, stripping these of electrons for more formations of such stars. So up to 1 billion years, stars were forming all over the universe. These stars further collect to form what is called as galaxies, which is the key factor, because the key factor for the occurrence of gravity and its further increase. So this is how from 0 seconds to the 1 billion years we see the continuous formation of stars and also the continuous formation of galaxies. This entire evolution, again you must remember, takes into consideration the fundamental particles called quarks and leptons. Number 2, these fundamental particles behave as per the 4 forces of nature, and number 3, as I told you, the fundamentals of quantum mechanics are applicable to understand their behavior with respect to the entire evolution of the universe. This is how a point of singularity has led to the expanding universe. In practical terms, how do we know that this Big Bang explosion has occurred? There are 3 very important developments that we can observe which can explain that the Big Bang explosion has really occurred. Number 1, it is observed that universe is still expanding. So the expanding universe is an explanation for the occurrence of Big Bang explosion, which has been observed by the Hubble. Number 2, we also see what is called as existence of the background radiation. It is because of the explosion, and it is also because of the continuous release of energy during various stages during this evolution, where there was release of continuous photons, which is the reason why the background radiation is existing. And number 3, the recent capture of what is called as gravitational waves. As I told you, the 2 objects, when they come together, they will exhibit this wave-like behavior also, which is not visible to the naked eye, which could not be experienced by the naked eye. However, the capture of these gravitational waves that we really heard in the previous session is also one of the key explanation and the key proof for the occurrence of Big Bang theory. So this is how Big Bang theory became the concept of astronomy, which would bridge all the questions with regard to the evolution of the universe. Have a glance at this entire Big Bang explosion as has been presented by NASA within these 27 seconds, covering the entire 14 billion years of evolution. Thank you.